In today's repetition course, we will have a look at the Diels-Alder reaction with a very instructive example. Here we have the electron-rich diene. Here we have the electron-poor dienophile. E should be the abbreviation for an ester moiety, for instance, an ethyl ester. So we have the reaction components A and B, and they will react in a Diels-Alder reaction. In a Diels-Alder reaction, always a cyclohexene moiety is formed, and in this case, if we get together like that, bond formation from here to there and from here to there as a concerted process, then we would end up with this product. But we have an alternative bond formation from here to there and from there to there, and this would be the cyclohexene, the substituted functionalized cyclohexene, which would result then. So we have a problem of regioselektivity. In addition, of course, we have also a problem of stereoselectivity. How are those substituents situated? What is the configuration at those chiral centers? Well, this we will discuss later on in the next video. Now we will concentrate on the regioselectivity. Well, we could just guess which of those two products is the one that is energetically favored at the end of the process. Well, this is energetically, thermodynamically less favored because we have here a somewhat crowded situation. So less favored out of steric reason. However, it might be kinetically favored, and indeed it is kinetically favored. How could we explain that and visualize that? Well, as I said, this is an electron-poor dienophile, and we have here in beta position a positive polarized situation because the conjugated ester is diminishing the electron density here. So it will attack somewhat faster with this position, with the delta plus position here at that diene compared to that position. It's still concerted, but during that approach, these two centers are more close together than those two centers, but in the end of the process, well, the bond length between here and there and here and there should be almost the same. So, how can we imagine why that positive polarized center attacks preferentially at this position? Well, just have a look what happens if we would protonate here this molecule. So, this pentadiene plus a proton, we have either the possibility to protonate here, it would result in this cation, or to protonate it there, this would be the result. So let us compare those two situations. In both cases we have allylic cations. However, in that case, on the left-hand side, we have an additional methyl group stabilizing the cation by its inductive influence. So this is clearly preferred. That means the protonation is here clearly preferred, and, well, also the attack of that positive polarized center here is preferred. It could be helpful to understand such a polarized transition state if we choose a Gedanken experiment. So, what if the reaction would not be concerted, but the CC bond formation here takes place first? Then we would get to this dipolar compound with the negative charge here at this position conjugated to the ester and the positive charge here. You can understand that as some kind of mesomeric structure, and the truth is in between that Gedanken experiment structure and the final product. This is then resembles that transition state. So this transition state is in between this structure and the final structure, with the delta plus here and the delta minus there. Not full charges here and there, as in this Gedanken experiment structure, but a partial negative and a partial positive charge there. Okay, now we clearly know this should be the kinetically favored and therefore anticipated product out of the reaction of those two reaction partners. And in the next video we will discuss what should be the stereoselectivity in that case. Thanks for listening.